excited to be here with you today and to talk about one of my favorite problems, which is cryptography and machine learning and cryptography and data. So this talk was inspired by personal pains and personal history. And so let me tell you a little story of an earlier version of Katharine that thought that she had solved a novel problem, and it turns out it was already a solved problem space for like probably about 30 years in cryptography. So I was working with a cybersecurity agency that was trying to advise several ISPs and other large network providers in Central Europe. And the goal that they had was, how do we find malware? And of course, they're like, deep learning is going to solve the problem. So they called up a deep learning person like me and the team that I was working with. And they said, surely you can make this a deep learning problem and we can find the malware if we just send you a bunch of our network traffic. Now, the problem is nobody trusted each other to actually share the network traffic. Because even though this was primarily internal network traffic and network data, the IP addresses that they used internally across the network would give away the way that they set up their overlays, their underlays, and all of these other things. And they didn't want to share it with their other competitors because, yeah, that's just proprietary and also sensitive data. This was pre-GDPR, so they weren't so concerned about PII, but they were definitely worried that others would peek at their data. And so some of the team that I was working with and myself, we thought, how can we solve this? And we wrote a bunch of algorithms and we wrote a bunch of math on whiteboards, and we came up with an idea where we would use a stream cipher and we would use a very special encoding and decoding mechanism that would allow us to save a few bits of information and also allow us to translate, so essentially encrypt. I use encrypt with heavy air quotes right now, to use this to encrypt an IP address and to get another IP address, and the first few bits of information still leaked information so we could use it to train in the machine learning model. And we thought this was fantastic. We had a name for it and everything. We called it homomorphic pseudonymization. We even started building a company around it. And we were very, very excited. And then some cryptographers got in touch with us and were like, you know, there's better ways to do this. And it's called format preserving encryption. And it's been around for like a really long time. Also, your method is somewhat insecure because this, that, and the other thing. So this is my own pain that we will talk about. And I want to save you time and energy by showing you some of the things that then later, after this point in time, I got deeper into the field of cryptography, had a chance to work with a lot of really great cryptographers, and we're going to talk about some of the things that I think might be useful even if you're just in software and you've never worked in the field of data science or data before. Some of them are really useful also if you've worked in data. So we're going to cover 3 different things today, 3 different problems. We're going to talk about how do you join data without peeking. So how do you join data sets without having a look at each other's data? How do you compute secret values with others? So how do values remain secret and you encrypt on them? And then how do you secure user messages? Originally in this talk, I had proposed that we talk about secure supply chains. That is not what I'm talking about today because I think it's really a lot more important right now, given everything that's happening in the world, that we talk about how do we secure private communication on channels. And so I will give some links at the end for the software verification chains. All right, so our first problem today is we're going to figure out where data overlaps without revealing the data. So we presumably have data set A and data set B, and these might be 2 companies or these might be 2 people. And we want to compare the data sets and we want to find where are these unique joins. And usually, so we can think of this in numerous ways. So one might be we both have phone books and we would like to figure out what contacts we have in common, right? That would be a user-to-user scenario. It might be that this is a third-party marketing department and this is our marketing department, and we would like to figure out, you know, what joint customers we have for a new venture or something like this, right? You should think about privacy here. This is only a crypto talk. I can't cover all the privacy problems. Or we can think about another problem, which is a problem that this type of cryptography is often used for in production systems. And this is the Google Ads problem. And Microsoft has a similar thing for their ads, and a few others, I think, use similar protocols now for their ads. So Google Ads, there's a really cool article called Private Join and Compute that Google announced many years ago. And it tells this nice story of a train service that a city is running. And in this story, the train service is trying to determine if offering more service on the weekends increases sales for the shop owners. And the shop owners and the train service, they don't want to exchange the user IDs because the city themselves would be then leaking a bunch of private information about the train riders, and the shops would be leaking a bunch of information about who actually buys things in their shops. But this is a thinly veiled story because the train service is Google Ads and the shop owners are websites. And so this is actually implemented and is one of the ways that Google Ads runs when they want to try to track ROI on ads, and they're sending all this data to shops, but they want to entice the shops to share that information. It's a win for Google, because if they find out that the people are spending a bunch of money, then Google can bump up the price for that ad. And maybe it's a win for the shop owners because they could see how much benefit there, something, value. Okay, so how do we make sure that this actually works and provides some guarantee of secrecy, right? And in that, I mean cryptographic secrecy, so that they can't peek at each other's values and figure it out. Okay, we're gonna get started at some of the fundamentals. Who's excited? Yes. Who's our favorite characters? Alice and Bob. Who's our enemy? Why is Eve our enemy? Just looks kind of evil. Hey, don't judge people by what they wear. All right, so Eve stands for eavesdropper. No, okay. All right, yes, claps are welcome. Okay, so we have Alice and Bob, and every crypto protocol starts with Alice and Bob because otherwise people get confused. So we can't change the names, it's always Alice and Bob. And Alice and Bob are always trying to do something together, and there's always malicious adversaries that are trying to do other things. In this case, we have Eve. These dotted lines represent trust boundaries, which is a cryptographic understanding that this provides security in some sense, right? So on this side, we have maybe Bob's hardware, maybe Bob's phone or something like this. And on this side, we have Alice's hardware and Alice's phone, and those are assumed to be private spaces. And then in the middle, we have the public internet or something else public, right? Maybe even a mobile network or other network. And this is where Eve can listen and record everything. And as Eve is listening and recording everything, we have to make sure that Alice and Bob can do what they're trying to do without Eve actually succeeding in their attack. Okay, so Alice and Bob in the Diffie-Hellman key exchange, which is different than some of the key exchanges that you probably know. The Diffie-Hellman is one of the best ones. You shouldn't use other ones unless you've really found a purpose for it. And so in the Diffie-Hellman key exchange, we have Alice and Bob. They agree here. The G stands for the generator that they agree upon, and the P stands for a very large prime that they agree upon. And those are either agreed upon in the standard and already known in public, or they send those over the public wire to each other and they both agree. They say, thumbs up, sounds good. All right, then they're ready to go. What Alice does first is Alice creates a private and public key pair. So Alice's private key is over here. Alice's public key is here in the clear, or not in the clear, but it's in the public space. Then those get shipped over to Bob, right? Bob does the same thing. And Bob uses the same generator and the same prime to do so. And Bob also ends up with a private and public key. Bob sends the public key back over to Alice. And now Eve has the generator, the prime, and both public keys. Cool thing about Diffie-Hellman is what Alice can do is Alice can take her private, or Bob's public key, her private key, and generate a new key. And it is the same key as Bob taking his private key and her public key and generating that. And this is due to, there's some modulo mathematics that happen in the background, and this allows this to happen. But even cooler, Eve cannot do this with any of the information that they have in this public space. it is computationally infeasible. Eve can figure out other ways to crack messages, right? Like maybe looking at Bob's phone and then comparing it with some text that was passed, right? There's other methods that Eve can attack, but Eve cannot, from this information here in the public domain, reverse engineer or even computationally, like a dictionary attack or something. It's computationally infeasible until we have quantum computers or something, and we can talk about that later. But yeah, these things mean that they have special principles. And why is this important? So now they can communicate using this shared private key, and Eve presumably cannot figure out any of this unless Eve gets even more information. And the cool thing about this is the Diffie-Hellman key exchange can actually also be used to join data, because with this protocol that happens right here, they can also actually agree on a way to encode the IDs that they share, and they can turn each row or each ID into a shared key. Then they can compare those shared keys, and it's actually not able to also, even with adding that information here, it's not able for them to reverse engineer each other's unless they have access to the other person's private key. So then at the end, they have a whole list of, essentially shared keys, and they can look and compare that. It doesn't leak any extra information other than the shared keys that they both have in common. Pretty cool. Wow, yeah, okay. All right, and so this is a pretty cool method. It's a little bit computationally heavy, and that's okay because there's new algorithms and methods. So the Diffie-Hellman key exchange is quite old, and it was used for finding private joins or private set intersection back in the 90s, but now we have better protocols. So now there's efficient protocols for all sorts of scenarios. There's different protocols or algorithms depending on if both data sets are massive. So you can think about like billions and billions of rows or terabytes of data, and you want to compare them. Okay, this is not, Diffie-Hellman is probably not the way to go, right? But there's ways that we can use oblivious pseudo-random functions to do so. And then there's ways that we can also do if you have billions and then I only have 100 or something like this. So when we have very unequal data sets, there's ways that we can optimize that as well. And if you ever had your browser tell you that your password has been hacked, it uses this. So if your browser like Chrome, I think in Firefox and a few others, they get the big leaked password data set, and then they make sure that it's encrypted in this way, and they compare it with saved passwords in your browser, but they're never actually then transmitting that data to themselves or to the server, right? So that's how those work. So private joins is what you're looking for here, or the technical term private set intersection. Please don't implement this in code. So I've seen even wonderful places to work. I've seen people be like, we're gonna create like a trusted server zone, and we're gonna send all the data to the trusted server zone, and then somebody's gonna compare it, and nobody's gonna get into it because we put the firewall and things like this. No. Just don't send the data anywhere joined. Instead, keep the data local and send, essentially use these protocols to find the joins. I also want to point out here that I think personally trusted third parties almost never exist. So I've worked a lot in the data sharing space. I don't think the idea of Trent, so Trent is in cryptography is who we call this trusted intermediary. I think in the real world, Trent is a myth. But this type of cryptographic protocol is really great for data sharing use cases, for cross-silo or cross-jurisdictional use cases, where let's say you need to share data with the United States and or Europe, and you don't want to get into a mess because of the different privacy and security regulations in those countries. So here I have an example. We might have messy data. We might have what we think is an incomplete hospital data set, an incomplete insurer data set, and an incomplete medical device data set. And we believe that patients that received this in a certain point in time might have been affected. And we might want to take some sort of grouping of the joins, or we might just want to take the full join of these data sets. And we could do so without shipping sensitive private health information around. We can instead choose an identifier that we can use and perform this in a cryptographically secure manner. Okay, we're going to talk about how do we compute on encrypted data. And we want to compute things together. And we want to do it without revealing any of our individual values. So this is a classic problem in computer science and cryptography, originally proposed by Andrew Yao in 1982, so quite a while ago. And Yao called it the millionaire's problem, but I have updated it for today's net worth, and I call it the Yao's billionaires problem now. And we have our buddies here. They're going to be having dinner together. And they have agreed that the richest of them all is going to pay for dinner. And they're not going to use Forbes net worth because they don't want to leak how much cryptocurrency value they hold and all of these other things, right? So they're going to secretly keep their net worth value, and they'd like to not reveal it to the others, but they want to figure out who has the most money, and then that person has to pay for the dinner. Well, this problem is solved in a field of cryptography or a subfield of cryptography that's called secure multi-party computation. And in secure multi-party computation, what we have is the ability to work across parties on encrypted values. So homomorphic encryption and secure multi-computation are the two big subfields that fall underneath encrypted computation. So encrypted computation is our big over umbrella, and we have SMPC it's called, or HE or FHE or PHE, which stands for fully homomorphic encryption, partially homomorphic encryption, or homomorphic encryption, right? And these are two ways that we can compute and we can get real results on encrypted values. So we take an encrypted 2, we add an encrypted 2, we get an encrypted 4, we can decrypt it, right? We can talk about the privacy of those methods, because obviously if we use a sum, then I could potentially reverse engineer. I could definitely reverse engineer your values, but in this field of cryptography, it means that we never have to decrypt when we're doing compute, and then at the end we decide who gets to see the decrypted values. Now, the trade-offs between homomorphic encryption and SMPC are that SMPC is very network heavy. It involves a lot of interconnectivity and communication, and homomorphic encryption is very disk heavy. So it's going to involve a lot of CPU cycles and compute energy. And also that the SMPC is focused on multiplayer, and the HE doesn't have to be in a multiplayer setting. So the homomorphic encryption you could do yourself. You could do if you, let's say, didn't trust your cloud provider, or you didn't trust a hosting provider and you wanted to go compute there. HE would probably be the best choice because you're just going to use a bunch of CPU cycles. But MPC is the best choice if you need to work with others and you have to share data and you have to compute something. And so it creates a graph. So always when we work in SMPC, we're working with directed acyclic graphs or DAGs. And it's going to create a big graph of the computation. And at some point in time, that graph is going to be compiled down into cryptographic protocols. And the protocols we use, we're not going to get into them, there's many of them, but the protocols we use are defined by the trust model and the number of parties. And we could talk more about that later, but it's kind of minute details at this point in time. But I see this as fundamentally transforming the way that we share data. And this was the field that I was working in before I joined Thoughtworks. We were building encrypted deep learning solutions using SMPC. Okay, so the cool thing is that SMPC has been going wild in terms of the amount of companies that are implementing this and using this. And this is because latency is now less problematic. So if you're in the cloud and you're in a similar data center as me, then for us to do the cycles and rounds of interactivity, then it's going to cost me less time. And it used to be that this was quite a lot of overhead, but now that everybody's shifting even their most sensitive data into the cloud, this means that this is actually starting to unlock use cases that before were infeasible because of the amount of interactivity we needed for the protocols. And so Cipher Mode is a company that just released last month their open source SMPC library. It's all built in Rust, and it also has Python bindings. And I just wanted to show you exactly how easy it is to use. So within this, we're first just going to create the graph. So I want to create the context. I use the context, which defines the number of players and the trust situation between those players. I use that to create my graph. Then I'm gonna set my input types. And I'm not gonna feed the data in now. This is just gonna be essentially a placeholder and a pointer, you can think of it as, that's gonna go get the data later when we're actually running the protocol. So I can set all of them even though I don't have access to all of them, and I can set millionaire 1, millionaire 2, millionaire 3. And we have very strict types, both in crypto in general, but especially in SMPC because we use ring arithmetic. So if we don't have strict types, then we can't actually decrypt at the end. We end up breaking the entire method. Then I'm gonna define a greater than operation, and I don't need a signed comparison because I know that both of these will be positive values and very large values most likely. Finally, I want to run that custom op, and then I'm gonna set my output as the final node of my graph. And so at this point in time, you actually have the graph, you're ready to compute. And at this point in time, what everybody would do if we were actually running this is everybody would be running a runtime, a secure runtime on their own infrastructure with access to this data. And we would then agree, all the players would agree to participate in this computation, and then it would execute. And it would execute at the cryptographic protocol level. So it goes through a compiler, and then it actually runs. It's pretty cool. Pretty cool that this stuff that I got. Okay. I'm very excited. All right, pretty cool that this stuff exists. It really, it's come a long way in a short amount of time, and I'm really excited to see how the field continues. And if you have data sharing problems, I encourage you to think about data sharing differently, not to send disks of data to each other in the mail. I know that this still happens. It boggles my mind. There's better ways for us to figure out how to share data in both a secure and a privacy-aware manner. All right, so I'm originally from California. I moved to Germany about 8 years ago, and all of the stuff that's been happening, obviously, in the United States since the past 8 years has been somewhat terrifying. And for this reason, I thought today that maybe it would be important to talk actually about end-to-end encryption and how do we promote and provide private and secure messaging for individuals. And this is especially important if on your platform you allow users to message you, you allow users to message each other, or you enable some sort of this back and forth sharing of data. I strongly encourage you to think about end-to-end encryption. So the Signal protocol was developed by the Open Whisper Systems team, I think first in 2014, and then it was later formalized in the Signal chat app. Signal is a really cool company and a really cool application that allows end-to-end encryption, and the end-to-end encryption runs by default. And the Signal protocol is a protocol that specifies all of the specifics of this interaction that happens on your phone when you use Signal, or on your desktop when you use Signal, and it's also now used at WhatsApp. Now, what's the difference between the WhatsApp one and the Signal one? Well, the Signal one is open source, the WhatsApp one is closed source and proprietary, and the WhatsApp one is not turned on by default, so we can all make our conclusions about that. All right, so the first thing that we need to understand, though, is what is a ratchet? Okay, so we got a ratchet here, and a ratchet is like a one-way key generator. So it keeps going one way, it can't go the other way. And what it takes as input is either we have an original start key, or we have the last key that we used. We have some private side information that comes, and then we have essentially another generator function. And this generator function allows us to then use this side information and the previous key to generate a following key, and it cannot go in reverse. So it is computationally infeasible, again, to reverse it without a significant advance in computational power. So this is kind of cool because if I use a ratchet and we have a shared key, so remember our shared key with the Diffie-Hellman key exchange? If we have a shared key, then you have the shared key on your phone and I have the shared key on my phone, then as long as we stay in sync and we step through this ratchet, we can keep actually changing keys with every message. We can keep changing keys with every message, and that is what happens on the Signal protocol, is every single message has a new key. Why is that so cool? It is very cool. It is very cool because if Eve gets extra side information, so Eve has figured out one of our messages, and Eve has then reverse engineered this shared key that we used on the Diffie-Hellman key exchange, and so now if we were talking the whole time using that key, if Eve was recording our whole conversation, then Eve can decrypt all of our messages. And that's bad. We don't like that, right? And so we have to be paranoid sometimes, right? Sometimes it's okay to be paranoid. And in this case, it is definitely okay to be paranoid, and Eve might have that shared key and still be listening. So this ratchet helps us move things forward. And the ratchet will be usually, in the signal protocol, we use two ratchets. There's a send ratchet and a receive ratchet. And both of them have to stay in sync on both sides. And there's a little bit of header information to make sure that we know which tick we're on. But what happens if Eve gets a hold of one of the ratchets? Because the ratchet algorithms and like the ratchet, the code that we use for it are going to be all open source. And if Eve can figure out maybe the side information, then Eve can essentially reverse engineer a ratchet. Not good. Okay, so the beauty of the signal protocol is that it's somewhat self-healing. In the sense that every once in a while, and it can be set up, I think, if you actually decide to use this protocol, you can decide what every once in a while means. Every once in a while, there's a full new Diffie-Hellman key exchange. And in the signal protocol, they don't just do that once, they actually do it 4 times in 4 different pieces of information. And so we then have completely new ratchets, because we have started with a new input, we have a new side channel, side information that we use. And so Eve, even though Eve might have been able to read 2 or 3 messages, maybe only on one side, if Eve only unlocked one ratchet, then it is reset again, it's healed again. And with this, it's called a Diffie-Hellman ratchet. With this new Diffie-Hellman ratchet, we are then able to have a new shared key that Eve doesn't have, and we can keep speaking privately. Pretty freaking cool. All right. Okay, so end-to-end encryption, why do we need it? Privacy and security of your users is really, really important. I hope I don't need to highlight how important, but please, like, if you have users in the US, just take care of them. I don't know if they can take care of themselves right now, to be completely honest. So just because you're not gonna look doesn't mean that other people won't look, doesn't mean other people at your company can't look, doesn't mean that somebody can show up, a federal authority, they need access to your servers, and. So there's a lot of things that can happen here. If you don't guarantee this high level of end-to-end encryption, it's gonna mean that there's information there that others can use. Right, and I think what we're trying to avoid now is information that others can use to potentially attack or harm our users, right? Or people that have trusted us to build trustworthy software for them. I don't know if anybody knows the word Datensparsamkeit. No German speakers? Anyways, Datensparsamkeit is essentially the German word for data minimization. And I want to share that because one cool thing about if you use end-to-end encryption and the few times that signal has been subpoenaed and brought before the US federal courts is the most information they have is the last 24 hours of timestamps, and that's it. They have no other information. They cannot supply any other information. And that's pretty cool. So making sure the less information that you have, the less of a chance that it's going to hurt your users potentially at a future point in time. This is also just good protocol or good high data hygiene to think about Datensparsamkeit or data minimization. Today was just a taste. Small advertisement. I know a team that is building cool open source software for menstrual tracking. They're called DRIP. They're based in Berlin. They're funded by EU funds and German federal government funds, and the data remains on the device. It is never sent anywhere else. In case you know anybody that might need to know, there's a small announcement. But really today was just a taste of the cryptography that's available. I have fallen in love with the field. Maybe one day I'll leave and go get a PhD instead of talking at these things. But for now, like, just know that this just a taste. You can dive deeper. It goes really far. It's really fun. If you ever liked math, crypto math is actually like way easier than you think, which is kind of crazy. And if you work in the data science or machine learning space, then it has some cool ways that you start thinking about numbers differently, which I can generally say has been really fun. Small reminder, never roll your own crypto unless you're working with a team of cryptographers. Use libraries. All of the things that I showed today are open source libraries that have been audited, that have been publicly reviewed. And I think that that's how we should keep it. I think that's really important. If you choose proprietary and closed source encryption code, then please make sure that it's been audited by an actual trusted third party, somebody whose reputation is on the line, somebody who has cryptographic expertise. And a small note that several of these problems have privacy concerns. Just because we have secrecy does not mean we have privacy. So when we compute on encrypted values or when we do other things like this and we reveal things, a lot of times we actually leak private information. So we have to think about protocols or methods, or it's not a protocol. We have to think about methods like differential privacy and other methods that we can use to add anonymization when it's necessary. And this can be combined with any of the things that we're doing here. Final note for everybody is cryptography, like any technology, is political inherently. And it's going to be used, especially a field like cryptography, is going to be used by political actors. So here I have a photo of the monument in Poznan. And Poznan is a place in Poland that's near the border with Germany. And Poznan is one of the places where they had a university of cryptanalysts that were able to break the Enigma code, and they were able to feed information to help essentially defeat the Nazis. So I share this because when we work in crypto and we work in software, we need to think about what we build, for whom, and against whom. And I just want us to always remember that and to think about it. Thank you very much.